Yeah, good morning, everybody. This was a good introduction to the topic, I guess. I would like to actually talk to you more about this issue of the non-CO2 climate footprint of aviation. And I think it's a very important, it's a very significant, it's a very timely topic to do this today. We've seen a lot of public attention around this topic evolving recently. We've seen policy pushes around it. So what are the questions that usually come up when we bring this topic to the stage? And what do decision makers ask us? And usually what I do see are two questions. The first one being, actually, what are these non-CO2 impacts of aviation? Where do they come from? And how large are they actually? And once we've answered that question, what can we do about it? Can we mitigate these impacts? And specifically, as you've seen in the video, there's been a lot of public debate about the question of mitigating contrails. So what can we do about that? I will try to give you some insights into both of these questions in the next about 15 minutes that I have here to speak to you today. So let's jump right into it and start with this question of what are the non-CO2 impacts of aviation? How large are they? And to start off this discussion, I always find it good to actually go to the source. Think about what actually is the exhaust of an aircraft. Here's a breakdown by mass of what actually comes out of the tailpipe of an aircraft. It's about 70% CO2, then there's some water vapor in there, and then there is about 1% by mass of different emission species, including nitrogen oxides, sulfur dioxide, unburned hydrocarbons, organic carbon, and black carbon, which is basically soot. And of course, we all know there are emissions that are related to noise, right? That's a community concern during takeoff and landing, specifically for the airport communities. One of the big hurdles towards building the infrastructure that the sector actually needs to accommodate its growth. I'm not going to talk about this today. This does not mean it isn't important. It's just I need to focus somewhere. So I'm going to move forward with these impacts, these emission products. And frankly, we're not interested in the emission product itself. We're interested in what the impacts are of these emissions. And most people these days are worried about the climate footprint. And the first and foremost issue there, obviously, are the CO2 emissions. We are all aware of the science behind that. You take fossil fuel out of the ground, take carbon out of the ground, you combust it, it leads to CO2 release, it increases the carbon concentration in the atmosphere, it leads to global warming. That's not what I want to talk about today. What I want to talk about are the additional, the idiosyncratic impacts that aviation has due to its emissions at altitude. And the first pathway that you've already seen in the video before is contrails. And there is evolving science that contrails on average are warming. But actually, you've also already seen what contrails are, right? They are white line-shaped clouds that fall behind aircraft. When do they form? They don't form all the time. They only form if the air is sufficiently cold and sufficiently humid, so that basically water can freeze onto particles in the exhaust of an aircraft. Only then that happens. Most of your time when you look up into the sky, you don't actually see a contrail forming. And in many situations, if you actually look up into the sky, it looks like what you see on this picture. You see a little bit of a contrail, but it evaporates right away. This is what we call a non-persistent contrail. We don't worry about this today because this contrail is not long enough in the atmosphere to actually have what we believe is a significant impact on the climate. What we worry about are contrails that actually persist for minutes to hours. They can retain their linear shape actually for long periods of time and look like what you see in this picture. But over time, they may also become diffused and become basically indistinguishable from a natural cirrus cloud. So why does the lifetime matter for the impact of a contrail? Well, for that, we actually need to understand how a contrail actually changes the energy balance of our atmosphere. And to be honest with you, this is a pretty established science because this is no different than what a cirrus cloud does, a normal cloud that you see up in the sky. It does two things. First of all, it reflects incoming sunlight back into space. Ever been standing in the shadow of a cloud? It's colder underneath. That's the science. A contrail is no different. And that's the cooling component of a contrail. The warming component of a contrail, well, you can observe this. Think about a winter morning. Think about a clear morning and think about a cloudy morning. It's warmer on the cloudy morning. Why? Because you have a cloud layer that insulates the atmosphere from heat loss. And again, a contrail is no different. It has this warming component. So for each and every contrail, it's very important to understand that the net impact of each and every contrail is situational, depends on the balance of these two effects, the cooling and the warming. They can be cooling, specifically during the day when you have this reflection component of sunlight. They can be warming, specifically at night when there is no reflection of sunlight. The average science tells us that the average contrail is warming. That does not mean that every contrail is warming. So keep that in mind as we move forward. Contrails are not the only non-CO2 impacts. Water vapor actually released into the atmosphere also has a direct warming impact, pretty well established. Nitrogen oxides emissions are kind of funny. There's a lot of different atmospheric chemistry processes going on that are related to NOx. I'm not going to go into the detail. All I'm going to tell you is it depends on how you look at it, whether you get a warming or a cooling effect. I'll come back to that. Sulfur dioxide, usually cooling. Black carbon, soot, it's a dark species, is basically warming. So this is the non-CO2 picture for aviation. One thing I do want to note is these emissions that you see here do not only have an impact on the climate, they also have an impact on air pollution, the quality of the air that we all breathe. How? This is mostly related to the NOx emissions of aviation, nitrous oxides. What they do is in the atmosphere, they lead to ozone and particulate matter formation. We breathe that in. What that does is it leads to cardiovascular, respiratory diseases and has mortality and morbidity endpoints. I'm not going to talk about that in much detail today, but it's important to keep in mind. So with that being said, you may wonder, how large are these impacts? And that's a good question. So let's talk about it. The way we usually tend to think about this question is very similar to a concept that you may have heard of, the social cost of carbon, right? That give you an idea of what the socioeconomic impacts of release of 1 unit of CO2 into the atmosphere is. We think about it sort of in an extended way here, and think about sort of the externality in terms of the dollars per ton of fuel burned. How do we calculate? It's very simple. You think about a ton of fuel burned from an aircraft. You think about the emissions that releases. You then think about the atmospheric processes that are related to that, so additional CO2 concentration, additional contrail formation, etc. You then think about the associated warming that comes with that, and then the associated socioeconomic impacts that are related to the warming. And that can be agricultural yield changes, that can be sort of human health impacts, that can be things like natural disasters. We can put dollar values to these things. So if you do this kind of analysis, how does the split of aviation climate impacts actually looks like? Here's our most recent assessment from MIT. It starts actually with a negative component on the non-CO2 side. NOx, negative impact, it's a cooling impact on that. And fuel sulfur, cooling effect, you saw that earlier. But then comes the warming element, the CO2 and the contrails, at a split of about 2/3 to 1/3. So what's interesting about this, if you look at this assessment, is actually the additional impact of non-CO2 on the CO2 impact is actually not that large in that assessment. And now you may ask, well, other people tell me different things, so what is this sensitive to? Two major things you need to keep in mind. First of all, if you do these types of assessments, you need to understand when the impact actually happens. So think about CO2. You emit CO2 today, it stays in the atmosphere for hundreds of years. So these warming impacts of a CO2 emission today stays in the atmosphere for hundreds of years. Think about a contrail, it's probably gone after 6 to 8 hours at the maximum. So its impact is accumulated very short term. So how do you now weigh the long-term impact versus the short-term impact? That's a question of discount rate, as you know. This analysis has a very low discount rate. So it gives a lot of weight to the far-out impacts of CO2. Therefore, the CO2 impact is relatively large compared to the non-CO2 impact. If you value the present more, then this changes in balance. What becomes smaller is the CO2 impact. The non-CO2 impact doesn't really change that much. So you actually get to a 50-50 balance or something like that if you actually increase this discount rate. That's very important to note, but we have to be consistent about it. It works by shrinking CO2, not by increasing non-CO2. So that's the first dimension on how this can change. The second dimension on how this could change is uncertainty in any of these elements. Let's talk about it. CO2. For CO2, the uncertainty doesn't lie in whether we understand the physics or the science behind what CO2 does on warming. This uncertainty is really about the monetization of these impacts, of the warming. But that is related to all of these impacts, so that really is a scalar for the entire analysis. So we don't have to worry about that. What we need to worry about are contrails. Here, the science base certainly remains uncertain, much more uncertain than for CO2. There's agreement on the warming effect on average, but there's uncertainty even at a specific situation under which you analyze a contrail. We do not know how large this warming really is. There is a lot of uncertainty. We need to acknowledge that. However, does it get into the way of decision making? I'm not sure. I'll come back to that. Lastly, let's quickly talk about NOx. People will have told you NOx is warming. It can be. Again, this is a very low discount rate analysis. If you actually drive that up, NOx can become warming. It's a funny thing because there are different processes going on, and depending on how you weigh things, you can really change the analysis. But the agreement is that NOx is not a major climate issue. Keep that in mind. However, that does not mean NOx doesn't matter. I told you earlier NOx is an air pollution issue. Just to give you a sense of the order of magnitude of the issue. The size of that issue is about 70% of the size of the climate issue. So don't say NOx is not an issue. It's just not a climate issue. So back to the contrails, because there's a lot of uncertainty. Can we actually do something about uncertainty using observation? There's a lot of work going on that, right? DLR, Boeing, NASA doing measurement campaigns. Some of the work that you guys do as airlines actually on gathering atmospheric data, the Mosaic samples, great data source. What we're doing at MIT is large-scale observation, okay? Trying to use satellites to analyze where contrails actually form. And we can do that at high temporal resolution, every 5 minutes. We do this right now, all the time. Here's how that looks. That's average contrail coverage over the US for the year 2018-2019 as seen from space. There's no model going on. This model doesn't know anything about flight paths, yet you see flight paths. These are contrails. At any given point in time, the picture doesn't look like this, though, because contrails only form at sufficiently cold and sufficiently humid. So at a given point in time, this is the northeast of the United States, it looked like this. This is the contrail detections, these black lines that you see over the map, live done on April 16th at 4:30 UTC. I could show you the picture now if I had the courage to do so. So this gives us situational awareness. It gives us a chance to learn. And it leads to the second question. How can we mitigate these impacts, specifically contrails? There's a range of things we can do. You can switch to different fuels that have lower water content or different emission speciation. You can think about changing the engine to form less contrails. You can think about convoying to overlap contrails. All of this, lots of science questions, long implementation timelines. What we can do much quicker is deviate flights around those regions where contrails form. How would you do it? Well, you could do it horizontally, same altitude, fly around it. These regions are horizontally large. You would have a lot of delay and a lot of additional fuel burn. That's probably not what you want to do. Instead, what you want to do is you want to adjust your altitude, because these regions are vertically very thin. Just a few thousand feet and you're in the good. That still means you have a fuel burn penalty. So we were interested how large this fuel burn penalty is. So we did a study. That's what we do as academics. 100,000 sample of 100,000 narrow-body flights around the globe. What's the fuel burn penalty for them to avoid contrails? Start with the dotted line that you see up there. You see about 1.5% of additional fuel burn gives you a contrail reduction of about 100%. But you don't have to touch all flights. These are just the flights that you touch. On fleet average, it's just 0.5% because you only have to touch 1 out of 3 flights. So let's do math. 0.5% additional fuel burn, even if it's a fossil fuel, means about 0.3% of climate impact for aviation, for a 30% reduction in climate impact from the Contrail reduction. This is a vastly beneficial strategy from a climate perspective. You could be a factor of 100 off in your Contrail assessment, it would still be beneficial. That's what I meant earlier with, does uncertainty have to get into the way of decision making? No, it doesn't. So why don't we do it today? Well, it's still a tough problem to avoid a contrail. Why? First of all, it's very hard to actually observe persistence. We can do it really well from space, but you actually can't do it well from an aircraft. People are talking about backward-looking cameras. Let me open it to you, it's not going to help. Because a backward-looking camera tells you whether a contrail is formed, but not whether it persists. So that does not work. What else can you do? You could try to put sensors on board of aircraft that actually gives you the right humidity and temperature information to actually see whether you fly through a region that is at risk of forming a contrail. Again, very tough, because we actually don't have small, low-weight, retrofittable sensors specifically for the humidity problem at altitude. Sounds funny? It is the case. They don't exist. Third, you could use forecasting model, right? Weather forecasts. The problem is, off-the-shelf weather forecasts were not made to predict contrail-forming regions. They're not calibrated for it, and if we compare to our contrail observation, it's not a great match. So there's work to be done there. And lastly, there is no one-size-fits-all contrail avoidance. It depends on flight. So does this mean we should just stop here and not do anything about it? I don't think so. And we've actually been working with Delta Airlines to actually show that it's not the case, that we can do something about it. What we've been working on is an observation-based method and framework to actually show how good contrail avoidance is, or how bad. Let's see what comes out of it. Observation-based, not model-based, pure observation, measuring what actually happens if we avoid contrail. Looking at it, not model. So let me show you how we do it. We start with our observation-based pipeline that actually helps us find regions where we see other flights form contrails. These are the blue regions that you see there. We can then overlay flight paths. So in this case, here I brought you an example, Delta 380 from Los Angeles to Washington, D.C., May 10th. You see it passes through this contrail-forming region. It's already somewhere over the mid-US, so this is kind of a live picture that comes out of our tool. So this flight is interesting. We need to look at it. So let's look at it. What we do is we take a cut through the flight path. Now we see whether we are also at risk of forming a contrail at the altitudes that we are flying in. And you see this flight flying at flight level 370. It's flying through a region where it is very likely to form a contrail because we have seen other flights flying in that region forming a contrail. That's a strong indication. So let's deviate around it. It's about 150 miles out. Let's give it a guidance. 4,000 feet down in this case. Yeah, you see the ACARS message there. Do it for 150 miles. And once the flight has done this, we can observe the outcome. Did the flight really not make a contrail? What is the net climate footprint? Because we can also observe the fuel burn impact. That's what we're going to do. Right now, we're simulating it together with Delta. We're testing the decision pipelines. We're going to do this as a large-scale observation-based study over the coming months. So let me leave you with 4 thoughts on how we can actually get to observable, verifiable contrail avoidance. Point number 1, I told you that contrail impacts vary by flight. We need to find ways to model that and capture that in a verifiable, observable way. We're not there yet. That's very important. Number 2, we need this observation-based data to really help us understand the costs and benefits of contrail avoidance based on observation, verifying, measuring. Once we have that, that gives us a lot to create the right policy and incentive structures. Third, we can then think about implementation, develop the decision support that we need, sensors, models. And last, concept of operations at scale. How do we do this if all flights try to do that? This is not a prioritized list. This is no particular order. We can do all of that in parallel. But these are the 4 thoughts I want to leave you with. Thank you very much for your attention.